Imagine for a moment, if you can, a world without modern farming. I mean, really think about it. No way to feed billions of people.
It's almost unthinkable, isn't it?
Exactly. And that world is basically one without ammonia. This chemical, it's the absolute backbone of the fertilizers that make our modern food system possible. It literally keeps us fed.
It's fundamental. But there's a catch, a big one.
Right. There's this kind of dirty secret behind it. The way we make ammonia now, it comes at a huge environmental cost.
We're talking about the Haber-Bosch process.
Yeah, Haber-Bosch, it was, an amazing piece of engineering back in the early 20th century. Solved a massive problem, grabbing nitrogen from the air, which is mostly inert, and turning it into something useful.
A real breakthrough for its time, but incredibly energy intensive.
Oh, incredibly. It uses something like 2% of the entire world's energy supply every single year.
Just let that sink in, 2%.
And the emissions. It's responsible for about 1.3% of global carbon emissions annually. Just this one process.
Because it needs brutal conditions, right?
Totally brutal. Temperatures over 400 degrees Celsius, that's, over 750 Fahrenheit, and pressure more than 100 times the normal atmosphere around us.
Yeah.
Just immense.
So, yeah, huge energy, huge emissions. Not exactly sustainable in the long run.
Definitely not. But what if? What if there was another way? A completely different way?
That's the big question researchers have been chasing.
And that's what we're digging into today. There's this fascinating new study, really groundbreaking stuff that might genuinely offer a green revolution for making ammonia.
Doing it without those extreme conditions.
Exactly. We're talking about making this essential chemical at, room temperature, normal pressures. Think about that.
That would be a game changer.
Totally. So our deep dive today is based on this paper called Cobalt-Based Catalyst for Ammonia Synthesis under Ambient Conditions via Transient Confinement. It was published in Nature Communications.
Nature Communications, very respected journal.
Yeah. And the team behind it, there are quite a few contributors. Karen Elvav and Mengqian Zhu are listed as contributing equally. And then Li Yang, Qingyu Wei, Jikai Sun, Xu Fang, Tai Yu, Xinyu Li, and Weiko Deng. They're from places like the Institute of Frontier Chemistry at Shandong University in China and the Key Laboratory of Precision and Intelligent Chemistry at the University of Science and Technology of China.
Right, strong institutions. So they're tackling this Haber-Bosch energy problem head-on.
Head-on. Okay, so let's unpack the Haber-Bosch challenge a bit more. Why is it such an energy beast?
Well, it really comes down to the nitrogen molecule itself, N2. It makes up, 78% of the air?
Something like that, yeah.
And it has this incredibly strong triple bond holding the two nitrogen atoms together. It's one of the strongest chemical bonds known.
Like superglue, chemically speaking.
Pretty much. Trying to break that bond to get the nitrogen to react with hydrogen to form ammonia, NH3, takes a phenomenal amount of energy.
So Haber-Bosch just throws massive heat and pressure at it till it finally gives.
That's the essence of it, yeah. For over 100 years, that's been the main strategy. Brute force, essentially. Use extreme conditions to overcome that energy barrier.
But the environmental cost is huge, as we said.
Exactly. So the question becomes, is there a smarter way, a way to apply the needed energy? More precisely, maybe not just heat, but something else, something gentler on the planet.
And this is where this new study gets really interesting. They're not using heat and pressure like Haber-Bosch.
No. They're using something called mechanochemistry.
Mechanochemistry. Okay, break that down for us. Sounds complicated.
It sounds fancy, but the basic idea is actually kind of intuitive. Think about grinding things, like in a mortar and pestle, but on a much, much smaller scale.
Okay.
They use mechanical force, literally physical collisions, to drive chemical reactions. In this study, they used tiny iron balls in a sort of a shaker, a vibration reactor.
Iron balls?
Yeah, like tiny ball bearings. And these collide with the catalyst powder, which in their key experiments was cobalt. These repeated collisions, this grinding action, actually provides the energy needed for the reaction.
So instead of heating everything up, you're sort of shaking the energy into the molecules.
That's a pretty good way to put it. It's using mechanical energy directly rather than thermal energy, but it's not just random bashing.
Right. There's more to it.
There is. The team and Mengqian Zhu did the key computational work here using density functional theory, DFT.
Okay, DFT, that's like supercomputer simulations of molecules, right?
Exactly. Powerful stuff. They used it to figure out what was happening during these collisions, and they found this effect they call transient confinement.
Transient confinement, okay.
So imagine two of those tiny metal surfaces from the balls or the catalyst powder smashing together really fast.
Right.
For just a tiny fraction of a second, like a microsecond or less, they create this incredibly small squeezed space between them.
A pinch point.
A pinch point, exactly. And if a nitrogen molecule happens to be in that pinch point right when it forms,
It gets trapped.
it's trapped and squeezed. And crucially, the theory suggests this allows the metal surfaces to interact with both ends of the nitrogen molecule simultaneously.
Ah, okay. So instead of just hitting one end, it grabs both.
Sort of like grabbing both ends of that super strong rope we talked about. And that simultaneous interaction, that squeeze, apparently weakens the triple bond significantly. It makes it much easier to break.
Wow. Okay, that's clever. It's not just brute force. It's like a targeted molecular level squeeze.
Precisely. A much more elegant way to apply the energy needed.
So they figured out this mechanism, and then they had to find the right material, the right catalyst for the job. You said cobalt.
Yes. They actually used those DFT calculations to model 5 different common metals: iron, cobalt, nickel, copper, and silver. They wanted to predict which one would be best at this whole transient confinement squeezing trick.
And cobalt won the simulation lottery.
Cobalt came out on top, yeah. The calculations showed it had the strongest transient confinement effect. It lowered the energy barrier needed to break the nitrogen bond the most from about 1.3 electron volts, which is pretty high for a reaction,
Right.
down to just 0.62 electron volts, basically half the energy needed at that crucial step.
That's a huge difference.
It is, and it fits well with this idea called the Sabatier principle in catalysis. You want a catalyst that binds the reactant nitrogen, in this case strongly enough to activate it.
But not too strongly.
Exactly. It also needs to let go of the product, the ammonia, easily once it's formed. Cobalt seemed to hit that sweet spot, that Goldilocks zone, with its interaction energy.
Okay, so the theory looked great. The simulations pointed to cobalt. But simulations are one thing. Did it actually work in the lab?
Oh, it worked. And this is where you get the real wow factor.
Riadas.
The team, led by researchers like Karen Orvev on the experimental side, they tested this cobalt catalyst. And they achieved an ammonia production rate of up to 13.7 micromoles per gram of catalyst per hour.
Which sounds technical, but is that good?
For these conditions, remember, 25 degrees Celsius, normal atmospheric pressure, yes, it's very promising. But here's the truly astonishing part.
Okay.
Their cobalt catalyst kept working, kept producing ammonia for over 350 hours, continuously, without losing its activity.
350 hours. That's like over 2 weeks straight.
Yep.
Just running and running at room temperature. As far as anyone knows, that's the longest lifespan ever reported for an ammonia catalyst working under these mild ambient conditions.
Wow.
It outperformed the previous best contender, an iron cesium catalyst, by about 10 times in terms of longevity.
That's genuinely incredible. Usually catalysts degrade, right? Especially new ones being tested.
They often do, yes.
Yeah.
Deactivation is a major challenge in catalysis. So achieving this kind of stability is a massive step forward. It makes the whole idea much more practical.
Okay, so how did they get it to last so long? Was it just the magic cobalt, or did they do something else?
It wasn't just the cobalt, although that was key. They used a clever two-stage process.
Uh-huh.
First, they did what they call pre-milling. They basically ran the ball mill with the cobalt catalyst only under pure nitrogen gas before introducing any hydrogen.
Why do that? That step activates the cobalt surface. It sort of prepares it, creates these active nitrogen species on the surface that are ready to react. Then, stage 2, they introduce the hydrogen along with the nitrogen, and the ammonia production starts continuously.
So like priming the pump.
Exactly. And they use some advanced analysis techniques, things like X-ray diffraction, XRD, and X-ray photoelectron spectroscopy, XPS.
More fancy tools.
Yeah.
Yeah.
They help you see the structure of the catalyst and what elements are on its surface and how they're bonded. And these tests showed the mechanical milling itself actually changed the cobalt structure on a microscopic level.
How so?
It created more active sites, more places where the reaction can happen. And it helped form favorable oxidation states of cobalt, like something called Su3+U, which seemed particularly good for the reaction.
Okay, so the milling process itself is crucial for preparing the catalyst just right.
Very crucial. But even with all that, they still ran into a potential problem.
Of course. Chemistry is never that easy, is it?
Rarely. They found that tiny amounts of oxygen impurities on the catalyst surface could react with the hydrogen to form water.
Water. Is that bad?
In this case, yes. Surprisingly, water turned out to be the main thing causing the catalyst to deactivate over time. It basically gummed up the works, blocked those active sites.
Ah, okay. So even with the pre-milling and the right catalyst, water was the enemy. How did they fight back?
This was another clever bit of engineering. They increased something called the space velocity.
Space velocity. Sounds like sci-fi.
Huh? Not quite. It just means how fast the reactant gases, the nitrogen and hydrogen, flow over the catalyst in the reactor.
So they just blew the gases through faster.
Essentially, yes. And that simple change had a dramatic effect. It extended the catalyst's lifetime from what was initially maybe just 12 hours.
Which is not great.
No. All the way up to that amazing 350 hours we talked about. And it boosted the ammonia yield, too.
Wow. Why did flowing it faster help get rid of the water problem?
Their calculations suggested that the faster flow made it harder for water molecules to stick to the catalyst surface. It sort of swept them away before they could accumulate and cause damage.
Neat. So fine-tuning the flow rate was key to that incredible longevity.
Absolutely. It shows how important optimizing the reaction conditions is, even with a great catalyst.
Okay, this is all super impressive science. But you mentioned a green revolution. What about the truly sustainable aspect? Does this process eliminate the carbon footprint?
Well, this is perhaps the most exciting part, the real mic drop moment from the paper, I think.
Go on.
They actually built and demonstrated a fully green ammonia synthesis system right there in the lab.
Fully green, meaning?
Powered entirely by renewable energy with zero direct CO2 emissions. They set up just 4 solar panels.
4 panels. That's it.
That's what they reported. And those 4 panels provided all the electricity needed for the whole shebang.
Which include?
Okay, get this. First, using electrolysis to split water into hydrogen, clean hydrogen. Second, separating pure nitrogen from the air, which also takes energy. And third, running the actual mechanochemical reactor, the vibration mill, to combine the hydrogen and nitrogen into ammonia.
All from 4 solar panels.
Wow. All from solar, start to finish. Water, air, and sunshine in. Ammonia out. Zero carbon emissions from the process itself.
That's the dream, isn't it? Sustainable ammonia.
It really is. And they calculated the energy consumption, too. At their lab scale, it was around 26.9 times 10 to the 11 joules per ton of ammonia, which they say is actually competitive with Haber-Bosch, energy-wise, at least at this scale.
Okay, that is genuinely mind-blowing. A potentially clean, room-temperature process powered by a few solar panels. It sounds almost too good to be true. What are the hurdles? What's stopping this from replacing Haber-Bosch tomorrow?
Right. Always important to ask about the challenges, and there are definitely hurdles.
Like scale.
Scale is the big one, absolutely. This research is fantastic, a brilliant proof of concept. But it was done in the lab, using what they describe as a homemade vibration reactor.
So not exactly industrial-size equipment.
No. Scaling up mechanochemical processes, especially ball milling, to the massive volumes needed for global ammonia production.
Yeah.
That's a major engineering challenge. We need completely new reactor designs, ways to make it efficient and cost-effective on a huge scale.
Okay, so scaling is hurdle number 1. What else?
Well, while they did an amazing job extending the catalyst life to 350 hours by managing the water issue, there might be other longer-term deactivation mechanisms we don't fully understand yet. And even though the overall process is low temperature, the impacts inside the ball mill, right where those collisions happen, can create localized hotspots of high temperature and pressure. Understanding exactly what's going on in those tiny impact zones is still an area for more research.
So the microscopic details still need some fleshing out.
Exactly, and that green root demonstration with the solar panels, phenomenal, a vital benchmark. But integrating all those components, electrolysis, nitrogen separation, the reactor into a reliable, efficient commercial system is another significant step. It's not just plug and play yet.
Got it. So incredibly promising, potentially revolutionary, but still needs significant engineering and development to reach industrial scale.
That's a fair summary. It's pointed the way very convincingly, but the journey to full-scale deployment has just begun.
Okay, let's try and wrap this up for everyone. This deep dive has shown some truly amazing potential for changing how we make ammonia. What are the absolute key takeaways?
I think the first one is clear. We now have proof of a cleaner path to ammonia. Mechanochemistry, using mechanical force, offers this radically new way, low energy, low pressure, potentially low carbon, bypassing Haber-Bosch's harshness.
Right. And second?
Second, cobalt looks like a real game-changer catalyst for this method. Thanks to that transient confinement idea, it achieved record-breaking stability over 350 hours at room temp. That's huge for practicality.
Definitely. And the third big takeaway.
Third, the green loop is actually possible. They showed it can be done. An entirely solar-powered system making ammonia from just air, water, and sunlight with zero carbon emissions. That's not just theory, they built it.
It really paints a picture of a different future for fertilizer production, doesn't it?
It absolutely does. This work from the team, published in Nature Communications, it's more than just a new catalyst. It feels like a potential blueprint for making essential industrial processes greener and maybe even more distributed.
Yeah, imagine smaller, local ammonia plants powered by renewables, closer to farms, reducing transport costs and emissions too.
Precisely. It could help decentralize production, making the food system more resilient and sustainable globally.
Okay, so this team used mechanical energy,
Yeah.
a sort of sophisticated grinding, to tackle century-old chemical challenge. It really makes you think, doesn't it? What other huge energy-guzzling industrial reactions out there making plastics, synthesizing medicines? Who knows what else might just be waiting for their own mechanochemical revolution? Maybe sometimes a precise little squeeze is all you need instead of a giant furnace.
That's a fascinating thought to end on. What else could we transform with this approach?
Definitely something to chew on. Thanks for helping unpack that today.
My pleasure. Really exciting research.